Hello students, this is Mr. Ezra. Today we are going to be working with z-scores, which might be something new for you. We're going to be using z-scores to compare with a normal distribution. So what is a z-score? A z-score is a pretty simple thing. I mean, the definition is it's just the number of standard deviations that some piece of data falls above or below the mean for that set of data. The formula for computing the z-score is pretty simple. You take your score minus your mean for the sample divided by the standard deviation of the sample. So it's score minus mean divided by standard deviation. When we have a normal distribution, we can turn that normal distribution into a normal distribution with z-scores. This is called the standard normal distribution. The standard normal distribution shows the z-scores on a graph where the middle is 0 because a mean is going to be 0 standard deviations above or below itself. And then as we go to the right, 1 standard deviation, 2 standard deviations, 3 standard deviations. We use the numbers 1, 2, and 3. And to the left, -1, -2, and -3. We can use z-scores to help us to compare when we have two different sets of data. For example, to calculate a z-score, if we have a normal distribution that has a mean of 50 and a standard deviation of 5, and I want you to find the z-score of 67, what we are going to do is to plug in the things that we know into the z-score formula. So I've written the z-score formula over here. I want to find what z is equal to. Well, my score is 67. I'm subtracting the mean of the distribution and then dividing by the standard deviation of the distribution. Now, when you put this in your calculator, if you put it in all at one time, you need to put parentheses around the subtraction so that your calculator does the subtracting first and then dividing, or you can subtract first, then divide by 5. But when you do this, you should get an outcome of about 3.4 if I have done my math correctly. 67 is 3.4 standard deviations above 50. Example 2, same thing. If you want to try this one on your own, pause the video and then start it back up to see if you got it right. So we have z equals, again, the score this time is 38. We subtract the mean of 50. And then divide both of that difference, we divide by the standard deviation of, in this case, of 5. Subtract first, then divide, or use parentheses around the numerator. You should get -2.4. Let's make sure that we understand what the positive and negative means. This is communicating that 67 is 3.4 standard deviations above the mean, while -2.4 is letting us know that the outcome 38, or the x value 38, is 2.4 standard deviations below the mean. Basically, negative means less than the mean, positive means more than the mean. Let's look at example 3. Test scores on the last major test were normally distributed. With a mean of 60 and a standard deviation of 9, you made a 54. So this is your score here. We have a mean of 60 and a standard deviation of 9. We want to find the z-score associated with this grade. So we're going to say z is equal to your score, ouch, 54, minus the mean. Well, obviously students did not do well on this test, divided by the standard deviation of 9. After subtracting 54 minus 60, -6, and then dividing by 9, you get a z-score of -0.6666667. It's basically -2/3, right? So this tells us that your score is less than the mean, but not quite a full standard deviation below the mean. Your very kind teacher decides to curve the grades. She is sad that so many students did poorly, so she wants to change the mean to 70. She's going to give that mean, that average, a 10-point curve. But and she's going to make the standard deviation a little less too. So 9 was kind of too spread out. She's going to change it to 5, but she's going to keep the z-score the same. Z-score the same. So here we have a new mean and a new standard deviation. And our z-score is going to stay what it was in that last question, which we rounded to be negative 0.6667. So your z-score on this test is going to stay the same. In this case, when we're filling in the things into our formula, we know z. We know that z is about negative 0.667. We do not know your test score because she's curving that test score, so that is the variable that we're going to leave out, minus the mean, which is a new mean of 70, divided by the standard deviation, which is a new standard deviation of 5. Now, in order to solve this, what we're going to do is multiply both sides times 5 to get that out of the denominator, right? After multiplying by 5, we get negative 3.35 about is equal to x minus 70 because the 5 canceled out. We are then going to add 70 to both sides so that we can solve for x. And what we get is that x is equal to 66.65 when we do the math. Now, this is a percent, right? Your score is a percent. So we might say that you scored, your new score is about a 67%. Just kind of rounding it up because I'm sure your teacher might round it up as well. All right. Very good. So let's look at example 4. Bill plays for the Silverhawks basketball team, and he scores 8 points per game, which is pretty good, I guess, for the Silverhawks, and because the team average is only 6.5 points with a standard deviation of 1 point. His friend Ryan plays for those dreaded Redhawks, but he's scoring the same number of points as Bill, 8 points per game, but his team average is a little lower at 5 points. But they also have a higher standard deviation of 1.5 points. They are arguing that they are equally as good as each other because they score the same number of points. But the question is, are they right? Who would be more valuable for their team? This is where z-scores really do a good job because we are able to compare Bill and Ryan relative to their teams by using z-scores. So we're going to use that z-score formula. For Bill, it would be his 8 points minus the mean for his team divided by the standard deviation for his team, which gives him a z-score of 1.5. So Mr. Ezra just noticed that he wrote the letter X here. That was a mistake. That should be the letter Z because we're changing this to a z-score. So if you'll fix that in your notes, and I apologize for that. Let's look at Ryan now. So Ryan's z-score is going to be his score of 8 minus a different mean of 5 divided by a different mean of 1.5. 8 minus 5 is 3. 3 divided by 1.5 is 2. So who has the higher z-score? Ryan. While Bill is only scoring 1.5 standard deviations above the mean for his team, the Silverhawks, Ryan is scoring 2 full standard deviations above the mean for his team. So Ryan is more valuable to his team because he is consistently scoring a higher number of standard deviations than the other players in his team. Example 5. So what we have here is at Eastview Pizza, where orders for delivered pizza are free if the pizza is delivered in more than 45 minutes. So that's kind of like our X value here that we're looking at. It always takes 15 minutes to prepare a pizza, and then it takes a different amount of time for drivers to deliver the pizza. Ben delivers a little more quickly at 12 minutes per pizza, but his standard deviation is larger at 10 minutes. Jim's delivery time is 15 minutes, but his standard deviation is also going to be a little bit smaller. What we're going to do here is make sure that we realize that this delivery time is going to have to be added to the time that it takes to prepare the pizza, since our 45 minutes is going to include the time of making the pizza and delivering it. So I'm adding 15 to both of those to get a new mean of 27 and 30. This table shows the statistics on the delivery times for the two drivers. So we're going to assume that these standard deviations are for the delivery time and the pizza making time together, and use those with our full amount of time to get the pizza to the customer. So for Ben, I want to know how many standard deviations he is. It's going to be above the mean for him to deliver a pizza in a manner that would cause it to be late. So we're going to say z equals 45. That's how long it takes it for it to be late, minus his mean time of 27, divided by his standard deviation of 10. Subtract first, then divide by 10 to get 1.8. So he's going to be 1.8 standard deviations. That's this line here is 1 and almost 2 standard deviations above the mean. You can see I've just put his mean time 27 at the bottom here, right? And then added the standard deviation. So plus 10 to get to 37, plus 10 to get to 47, plus 10 to get to 57, just like we did in previous lessons. And we're going to subtract 3 standard deviations to the left by subtracting 10, subtracting 10, subtracting 10. Now, technically, it's not possible for him to have a negative delivery time, so this would never happen, but we're going to include it because it's under the curve here. Now, Jim, on the other hand, his z-score is going to be based off of the 45 minus his time to deliver divided by his standard deviation. His standard deviation is smaller, so it may take him a little bit longer, but he's also more consistent in his time. When you subtract first, then divide by 6, you get 2.5 here. Well, even though Ben is delivering quicker, 2.5 is further to the right than 1.8. The 45 under both of these curves is the same, but because his mean of 30 and his standard deviation of 6 gives us different numbers, 45 minutes is further from the mean. We want to know what's the probability that the pizza would be delivered late, right? Who's going to be giving away more free pizzas? Well, we can actually find this probability using a tool that we discussed in a previous lesson. We could say normal CDF. Remember, in your calculator, you are going to hit second VARS. You're getting that secondary command distribution, DISTR, and you're going to choose normal CDF. You put the lower limit, which in this case is 45. The upper limit has to be a really big number like infinity, which we can't put in our calculator, so put 1E99. And then the mean of that distribution and the standard deviation of that distribution. When you put this into your calculator, and you get 0.0359. So he's going to be giving free pizzas about 3.6% of the time. When we look at Jim, we're going to use that normal CDF again, but we are going to have a different mean and standard deviation. So we're still saying to the right of 45, but a new mean of 30 and a new standard deviation of 6. For Jim, we get a probability of 0.006, which is about 0.6%. So this area right in here is about 0.6% of the time he's delivering free pizzas. This area right here is about 3.59% of the time. Who is going to be delivering or giving away more free pizzas? Ben is going to be delivering or giving away more free pizzas. Ben is the answer to this question, and this is our justification for how we got there. Example 6. This is our last example for today. Lewis earned 85 on his biology test, and that test had a mean of 79 and a standard deviation of 3. Lewis earned an 80% on his history test with a mean of 76 and a standard deviation of 4. So I'm going to pull out all of those scores and statistics here, and we're going to assume that these test scores are normally distributed. And we are asked what percentage of the class was below Lewis on the biology test. So if we think of this normal curve here, What we're asking is if Lewis made an 85, what percent scored below him? Normal CDF is how we've learned to deal with this question. Since it's less than, we're going to go from our lower boundary or lower limit of -1E99, which is the biggest negative number our calculator can handle. Our upper boundary or upper limit's 85. The mean for Lewis's biology test was 79, and the standard deviation was 3. So after putting this in our calculator, we find that he did quite well relative to the class. He did better than 0.9772 of his classmates, which is 97.72%. And as for percents, we should convert our answer to a percent. We also want to know, well, what percentage of the class was below Lewis in history? We're going to do the same process, right? But this time we have a different test. We're looking to the left of 80 instead of 85. And we also have a new mean and a new standard deviation, but we're going to use that same normal CDF command to find the area under the curve, or the percentage. And this time we get 0.8413, which is 84.13% about rounded. Now we can see from this that relative to the class, he did better in biology, because he did better than more students, or a higher percentage of students in the biology class. But when question C says, on which test did he do better compared to the rest of his class, the justification that we usually give here, even though we already know the answer, is to find the z-score. So his z-score for biology is going to be his score of 85 minus the mean of 79 divided by the standard deviation, and we get a z-score of 2. Whereas in history, 80 minus 76, 4, divided by 4 is 1. Well, which is the higher number? 2. He did better relative to the rest of his class in biology. So it was Lewis did better on the biology test relative to the rest of his class. Now, he also did better in the raw score. But we can't just look at the raw score when we're doing these comparisons, because the standard deviation and the mean of the class where it falls in relationship to those things could mean that a higher raw score is not the highest score relative to the class. In this case, it is. Well, students, that is it for today. We've talked about z-scores. We've talked about comparing distributions, different ways to do that. I hope that these ideas make sense to you, but of course, if you have questions as you're practicing, please ask them, and I'll see you in class.